The next talk will be given by Jean-Luc Jaffard from a French company called Prophesee. Jean-Luc has worked a very long time for STMicroelectronics, where he initiated and developed the activities on imaging. So it's a field that he has been involved in for a very long time. He left ST in 2014 to join a consulting company called Red Belt Conseil, and joined Prophesee, a French startup specializing on biomorphic sensors to detect events in image sensors. And he will share with us the activities of the company and how the company sees opportunities in the field of 3D stacking, which has been a main field of Nanoelec, as you mentioned. So as I mentioned before, Jean-Luc is intervening remotely, so we will give him the floor now.
Okay, I will start. So, okay, good morning, everybody, and sorry for not being with you this morning. So it's a pleasure to present the activity of Prophesee and the interest of the company to join a consortium like the 3D Nanoelec. Okay, so first of all, just to introduce who is Prophesee. Prophesee is a French startup company created 5 years ago, which is exploiting a technology developed by some UPMC and Vision Institute in Paris, which try to mimic the behavior of the eye of the retina and the way the information are transferred from the eye to the brain. So the company is now around 100 people. We are mainly based in Paris with a site in Grenoble and the sales and marketing site in US and Asia. So we are doing 3 types of things today. We develop a hardware and software component. We develop a solution with a complete camera, and we have a complete development system, including the camera and the processing. And the first component are now on the market with industrial product. So this technology is it's an imaging technology, but we call it is an imaging sensing technology. So that's been for many years the imaging industry has focused on improving the image quality, and we have seen the evolution over the last 15 years with the cell phone, which has pushed this industry and the technology to get a very good result. We are not really in this domain. We are domain of the sensing, so that means where the importance is the action is not the quality of the image. I'm not saying that this does not require efficient sensor and performance sensor, but the purpose is really to sense the image and not to display and print the image. So what is the base of the technology behind that is that we consider in an image or in a video, there are a lot of redundancy and a lot of inconsistency in the image. For example, here in the baseball, you can see on the top part of the image, there's basically oversampling. So that means we cannot see the detail, and the detail of the image will be limited by the optics and the resolution and the sensor. But on the other side, around the arm, where there is a very strong motion content, the image is, with a classical sensor is undersampled. So that means all of that thing that fine for a normal image, it's maybe acceptable, but for when we want to have a very fast motion detection, interpretation, and optimization is not the ideal thing. And this undersampling will create a motion blur that will create distortion of the image. When the oversampling part will create a redundant, useless data, okay, which are, let's say, for high resolution sampler may occupy a lot of bandwidth and so on. So what is an event sensor? The event sensor is moving from if you look on the left side, the standard camera, we frame the sensor and we sample this image on a fixed time with the classical sampling base. On event sensor, the samples, the pixels are samples only when the pixel detect a change. So that means in a scene where there is no change, no motion in the image, basically the sensor will not deliver any information. So the benefit of that is that we can, in case of the change in the image, we can generate a very fast response, and that's eliminate blur and this kind of thing. So a totally different concept where we have not something repetitive, we move from something which is asynchronous to asynchronous, and that's make possible to reduce drastically the amount of data, and in the same time to have a very fast response. Okay, so the same thing. Sorry, I think the PDF will not show the video here. Yes, it's the case, and sorry for that. But in fact, this type of a sensor allow to transmit information in permanence. So that means if there is a change in the scene, the sensor will detect this change and will continue to send information. So that means you will not have a discontinuity in the generation of frames. So if I can make an illustration of that, if you have a camera in a car, this camera, a frame-based camera, we sample every X frames, so every X 10 times or X 100th time per second the image. And during this time, the car can move and something can happen. With an event sensor, we will monitor continuously the change of the image. So that means it will generate a lot of events, but only on the part which is changing. So that's make a very complex, different way of approaching the image. The benefit of the technology, we see four major action. Detection is that, as I mentioned, the detection can be extremely fast. The prediction is that we can detect only the part we change. So that means it's pretty easy to make interpretation of change. The robustness is that each pixel is independent, and therefore we can have high dynamic range, independent pixel to pixel, and efficiency is a limited amount of data transmitted from the sensor. Okay. I have a bit of problem with that. Okay. Fine. So where do we find this technology? We can find this technology in industrial automation, where fast motion detection is required. We can find that in IoT, where the opposite is low power, and automotive. I mentioned about that, which is the speed. Now, if we look what happened over the last, let's say, 20 years in the sensor. So on the CIS sensor, we move first from let's say the first concept in the late 90s, what we can do the sensing and the processing inside the chip. So basically, we have the sensor plus the image signal processing, and attached to that in the system, there was a processor somewhere. After that, we move to a step where we separate the image signal processing, which is the image reconstruction, from the sensor itself. And we had solution with basically three components: a sensor, a coprocessor for image restoration, and a processor for the main topic. And step by step, we move to something where we go back to a sensor plus the processing of the ISP, thanks to the first level of stacking with two wafers. And then we can start getting something processing close to the sensor. And the way we see in the future is that, in fact, we will continue this integration, but not having let's say the first level of processing, but having the compute close to the sensor. And that's where we'll continue this integration. So we see over the year that the initial idea of having all the processing close and inside the same sensor will happen now, I think, in second half of the 2020, with a full automotive sensing and processing system. Okay, so I will quick around that. That is the evolution of the 3D image sensor technology, with we move from the front side to the back side, first with the TSV connection and then to hybrid connection. We'll come back a little bit later on that. This is not new in terms of image sensor. The first 3D hybrid sensing sensor was introduced in 2013 with the TSV stacking, and move step by step with the hybrid stacking. Okay. Now, as I mentioned before, we have pretty a lot of processing in our pixel, and I try to make a distinguo here between what I call the embedded processing imager and the in-pixel processing imager. The embedded processing imager is the sensing, but okay, it requires small pixel, advanced technology. It requires imager and CMOS compatibility to have some local processing, and it's very often driven by the small pixel size. The in-pixel processing imager is that it's again a CIS sensor, okay, but is also an SoC imager, and each pixel embarks a lot of components. So that means when you have a pixel with a lot of component per pixel, the shrinkability of this pixel size is questionable, and very often it's ended with a very large component size with very large optical format and basically not a very cost-efficient solution. So how to address that? So the 3D process for imager address this problematic, and there are two. If I compare again the embedded processing imager with the in-pixel processing imager, the embedded processing imager, basically what we see, the CIS layer is mainly composed of the pixel array, and all the processing, either analog or digital, is put on the CMOS wafer, and we are generally speaking about, let's say, hundreds or thousands of contacts between the two wafers. On in-pixel processing, the situation is slightly different because all the size of the CMOS process of the bottom wafer below the pixel array is used for the in-pixel processing. And the extra processing, either analog or digital, will occupy an extra place on the bottom wafer. So that's mean just to bring one point, which is okay. That means there will have a question of optimization between the two wafers. And here we are speaking about hundreds K to millions of contacts between the two wafers, depending of the resolution of the sensor. Okay, now as soon as we speak about those two wafers, and that I mentioned that potentially there is a space in the top wafer to do something else, that bring the question: what is the best choice? What can be done in the first wafer, in the top wafer, and what can be done with the bottom wafers? So that's immediately bring a question: is there is a room here to optimize not only the process, but to optimize the partitioning and therefore the cost of the solution. Okay. So now, coming back on the Prophesee pixel. So I illustrated on the left a pixel that we have implemented in an FSI CIS 180 nanometer process. It's a 15 by 15 micron pixel, and we have a fill factor of 20%, and we have around 50 component per pixel. So we can, just looking at the layout of this FSI pixel, the interest and the benefit of the stacking is immediate. We can see that if I just move all the component to the bottom wafer, I will reduce by 4 the pixel size and our fill factor close to 100%. So that means here we are doing really a lot of processing inside this pixel. Okay, so it's fine, but the partitioning between the two wafers is important for the processing, but is also a question mark for the pixel itself. So here I try to illustrate the first stage of our pixel, which is a diode with an amplifier and a few components. So there are different ways to split that, what we do in the top and what we do in the bottom wafers. And I put some red dot here to see, okay, we could put the connection between just on the top of the diode, we could put the connection on the output of the amplifier, and so on. And you see immediately that that's generate a lot of discussion around the optimization, because where the split will happen between the two wafers will have an impact on the best way to optimize each of the process for the top and bottom wafers. So here, I will go quick on this slide, but just to illustrate the benefit from a system point of view to have the right partitioning. I've looked at the ratio of the size of the pixel without, on FSI, that means without a stack, so what we can get with a stack with the minimum diode. And you can see that just playing with the ratio of integration, the way you reduce from the FSI to the stack, can have a big difference on the capacity you can put inside the same optical format and the resolution that we can reach inside the same optical format. And it can be very significant. So if I take two examples, you have a diode of 2 micron with a fill factor of 16%, I can put in a half inch, you can put roughly 1 million pixel resolution. If I put a 4 micron diode, okay, with a fill factor for close to 100%, which is the case in case of stacking. Basically, with a 1-inch format, I will put a roughly 7 megapixel resolution. So you see that the compromise between the integration between the two wafers is very important for the cost of the total solution, because it's not only the cost of the solution of the silicon, but it will be also the cost of the optics and mechanics and so on. Okay. So in the ideal world, I would say that when you are a designer, a sensor designer, that you want to use a stack pixel process, you should look at different things. Basically, the size of the diode and its performance, the fill factor, the ratio between analog and digital, okay, the sensor device, same thing, the CIS wafer and the CMOS wafer, which technology node are the best. Depending of the application, you may have interest to use a much more advanced CMOS node, the bottom wafer, than the other. Okay, and another thing which is important is what is the CIS process and the CMOS process compatibility. In the case of a stack, basically we can separate the performances and the constraint of the detections part with CIS and the CMOS can be completely separated. Obviously, from an application point of view, stack and BSI has an impact of cost because we are putting two wafers together. So that means it requires even more constraint on the quality of the design, because at the end, the total cost of the chip will be the combination of the sum of the cost of the two wafers multiplied by the yield of each wafers, including the bonding of the two wafers. So a new challenge for the designer people to be sure that they achieve the right technology. I think one thing is okay. So now, if we look at for the future, we think that more and more the sensing will become something standard, I would say, but the differentiation and the added value will come from the computing. And we are convinced at Prophesee that the evolution of at least the sensing sensor that we are developing will embark more and more processing locally. Because one very simple concept on that is, if you have a sensor which is extremely low power, why are you going to burn a lot of power just to transfer the information? And why on a sensor which is totally asynchronous is there interest to do synchronous processing? Is maybe a benefit to do asynchronous processing and to have in the same time the power consumption and the size and the amount of data transmitted are optimized. And is why we think, and we are convinced that the future, let's say, of this of the technology for us will go to multi-stack technology. Or not, there was a first implementation on triple stack that was mainly used for slow motion, and there was done with one CIS wafer, one DRAM, and one digital wafer. On our application, we have a slightly different view. We think that the first level will still be an optical wafer and optical performances. The second one will be at least a CMOS, but the third one may be and also a CMOS with a different technology node, which something will be very low power, very, very high density to make all the computing local. So in the conclusion of my talk, as you see, that's seen from the user point of view and for the application point of view, there are multiple ways to define an intelligent sensor and the way to use the 3D process variant. The benefit we see is that with such approach, the CIS, that means the sensing and the CMOS process wafers, can be totally optimized independently. So that means that we can have evolution of one of the two wafers depending of the application and the product complexity. Okay. Obviously, the challenge of the design will be that the design will have to cope with the combined process spread of the two wafer. Okay. The 3D BSI PIX process build for company for solution when we have in-pixel processing, obviously, is the route to improve the fill factor and you reduce the pixel size and to make the technology more scalable. Okay. The challenge of how you fit the processing between the two wafers is really something that the designer have to think about at the very early stage of the design. And obviously, Even if today the offers are limited, what we think in the future is that they will have more and more different type of offers, either on the sensing part or on the CMOS part, that can be used to optimize the solution. So thank you for your attention. So if you have any question.
Thank you very much, Jean-Luc. We had one question from David that we can take.
Yes.
If the interface between the pixel processor and the digital compute is not a frame buffer, what is it?
It can be, okay, it can be, well, when we have an event sensor, okay, event-based sensor generates. Okay, so I will answer. I hope you switch off. Okay, between the pixel processing and the digital processing, it can be, we generate the stream of the event, and this event has to be processed, okay, as a stream. I'm not saying that in the compute there is no frame buffer, there is not high amount of memory, but is to compute the event is not to compute the image. It's not exactly the same thing.
Okay, thank you very much, Jean-Luc. So we can move on to the.
Question.
Oh, there is another question from Jean-Marc Talbot. What are the main markets of Prophesee? Are there already systems embedding Prophesee chips in industrial applications or industries?
The first market that would be addressed by Prophesee is the industrial automation market, and there are camera available. The first industrial camera available on the market is coming from a German company called Imago. You can buy any camera you want from with this our technology inside.